how many different partitions of the number 6 are there into distinct parts, and how many into odd parts. Remember what a partition is? Maybe not at this point. We introduced this at some point last time. So I'll leave the poll open. I'll let you put in your answers if you remember. So partition is like a way of writing. So partition of 6 is a way of writing 6 as a sequence a1 plus a2 up to some number ak, where the sequence is the biggest number comes first, the second biggest number comes second, or maybe they're the same size. It doesn't really matter. AK is the smallest number, and all of them are at least 1. And the parts are called, these things AI are called the parts of the partition. So that's a part. That's the first part, second part up to the kth part. So if we're trying to partition 6 into distinct parts, there's various different ways to do that. Here's the simplest way to. So distinct parts, I just mean all, every 2 parts in the partition are different. Well, why don't we just start writing all the partitions and see what happens? So if I want to write 6, I can write 6 as just being equal to 6. So that's a partition into 1 part. I can write 6 as 5 plus 1. That's a partition into 2 parts. I can write it as 4 plus 2. Or I can write it as 3 plus 3. This one's no good for us because we're trying to use distinct parts. So 3 plus 3 doesn't count. And 2 plus 4 doesn't count, right? Because that's not a partition, right? That partition, you have to have the biggest number has to come first. And if I do 2 and 4, then that doesn't have that property. So these are all the partitions into 2 parts, 2 parts. 1 part is just 6. If I do it into 3 parts, I've got, say, 4 plus 1 plus 1. I've got 3 plus 2 plus 1. I can't do 3, 1, 2. That doesn't count. I can do 2 plus 2 plus 2 would be okay, except that I'm saying that the parts have to be distinct, so that doesn't count. Let me know if I'm missing any here. So because these are all the partitions. These are all okay if I'm talking about partitions, but if I'm talking about partitions with distinct parts. So distinct parts means that no 2 parts are the same. The same size, I guess. So maybe this wasn't, maybe what I meant by distinct parts wasn't completely clear. I guess distinct could mean, yeah. Anyway, so that's what, at least that's what I intended, was to mean that all the parts are different sizes. If you didn't kind of get that from the question and it made your answer wrong, then that's okay. Okay, so can also do so into 4 parts would be you can do that into 3. Sorry, I'm trying to get the chat again. Sorry. Yeah, good point. Well, obviously not paying that good attention. 4 plus 1 plus 1 wouldn't count. That's a good point. So now if I do 4 parts, I can do, so yeah, do check what I'm doing here. So 3 plus 1 plus 1 plus 1 works, but it doesn't have distinct parts, so that's no good. Actually, if you think about it, if you break it into 4 parts, there's going to be no way to do that with distinct parts, because maybe there's a kind of pigeonhole reason, but yeah, if you go through all the cases, you won't be able to do it, because I can do 2 plus 2 plus 1 plus 1, but that's also no good for multiple reasons. And then also if you do it into 5 parts or 6 parts, it also doesn't work. So actually these are your only 4 options at the end, which are, yeah. So the answer is 4. And actually so the second part of this question asks for odd parts. And if we kind of go through these things, well, yeah, maybe I don't want to, but anyway, this one's into odd parts. That one was into odd parts that I scratched out. That is odd parts. I could also do, I think the only other one into odd parts is 1 plus 1, like 6 times. 1, 2, 3, 4, 5, 6. So the number of ways to do it into odd parts is also equal to 4. So the answer to both questions is 4. And what we're going to show today, or part of what we're going to do today, is to show that this is not a coincidence. That for 6, the number is 4 for both of these questions. What we're going to show is actually for any number, the number of partitions into distinct parts is always equal to the number of partitions into odd parts. So this is not a coincidence that the same number both times. Right. So again, remember we let Pn be the number of partitions of n, just to remind us. And this is review from last time, but it's worth kind of reminding you of this. So the generating functions for the number of partitions, well, of n is, well, on one hand, you could just write it like this. If because if Pn is the number of partitions, then this is, the generating function is just defined like this. But we came up with this kind of weird formula for the generating function. And the idea was that, like, if you take a partition of n, that partition has some number of ones and some number of, which might be 0 ones, right? It might have 0 ones or 1 1 or 2 ones, etc. It has a certain number of 2s and then a certain number of 3s and so on and so forth. And basically the purpose of, so the way this product works is that, so if I want to make x to the n from this infinite product, I have to pick something from here, multiply it to something here, multiply it to something here, and I've got these dot dot dots, so I'm multiplying it to something in the next thing, which is 1 plus x to the 4. So like each factor here is, of the form 1 plus x to the m for some m, plus x to the 2m, so x to the 8 here, and so on, right? And to make an x to the n, I have to pick one thing from every factor and multiply them in such a way that the exponents of those things add up to n. And picking a copy of, like, from the first factor, if I pick, let's say, x to the k, if I pick that from here, that corresponds to having k ones in the partition of n. So if I choose an x to the k here, that corresponds to having k ones. If I choose, so here I'm either going to choose x to the 0 or x to the 2 or x to the 4, and choosing x to the 2k here corresponds to having k2s. And in general, if I choose x to the km from the factor which looks like 1 plus x to the m plus x to the 2m dot dot dot, if I choose x to the km from there, that corresponds to having km's in the partition. So this takes a little bit of time to wrap your head around, but yeah, it's worth thinking this through. I'm not sure that there's any more explaining I can do to kind of give you the intuition here, but basically this is kind of the idea. So this gives us this as our generating function for the number of partitions of n. And this is because, so here this factor is 1 over 1 minus x. This one is 1 over 1 minus x squared. And in general, you're going to get 1 over 1 minus x to the m. And you just multiply. So this product, this symbol means you multiply this over all values of m. Okay, so this is the generating function for the number of partitions of n. We want to look at, so what I want to do is, we want to prove this theorem that the number of partitions into distinct parts is equal to the number of partitions into odd parts. And the way we're going to do this is by modifying that generating function to get a generating function for these sequences. So the sequence of partitions into distinct parts, or the sequence of the number of partitions into odd parts. And then what we're going to do is show that actually, so we're going to write down two generating functions. We're going to write down a generating function for this thing, so partitions into distinct parts. We're going to write down a generating function to partitions into odd parts. Then we're going to do some algebra, and we're going to show that those generating functions are the same function. And if you know that two sequences have the same generating function, it tells you that those sequences must be the same, which tells you that the number of partitions into distinct parts is equal to the number of partitions into odd parts, which is kind of a little bit magic, I think. So let's kind of come up with the generating function. So first of all, let's do the odd parts. So I want to know how many partitions are there of the number n into odd parts, so I'm not asking how many are there. I'm not asking you to count it, but all I'm asking is for the generating function. And you can get this by just manipulating the generating function we got for all the partitions. So the first factor counts the number of ones in the partition, right? So it's 1 plus x, x squared, etc. And then what we do is we think, okay, if I'm partitioning into odd parts, then I know that the number of 2's in the partition is 0. So you can either think of that as saying, in my previous generating function for all the partitions, you can think of that as saying, okay, I'm always choosing a 1 from that factor, because 1 is x to the 0, so that means there's 0 parts of size 2. Or you can just think of, okay, I just don't include anything about parts of size 2 because there aren't any parts of size 2. So either way, it doesn't really matter how you want to think about it. But in any case, what you do is then you put a factor which counts the number of parts of size 3. So the number of parts of size 3 is either 0, or there's 1 part of size 3, or 2. So 1 corresponds to an exponent of x cubed. 2 corresponds to an exponent of x to the 6, and so on. Then you have parts of size 5, parts of size 7, parts of size 9, and so on. Okay, so if you understand the generating function for partitions in general, then it's a small step to understanding this generating function. Right? So we just include the odd factors. And this I can write as, so the first one I can write minus x. This one is 1 over 1 minus x cubed. This is just by the standard kind of generating function we understand, which is the geometric series. This one's 1 minus x to the 5. And in general, we get that. So if you think about it, we're doing all the odd powers. And so this is the product from m equals 1 to infinity of 1 minus x to the, so let's call it 2m minus 1, right? So if you think about m equals 1, that gives you an exponent of 2 times 1 minus 1, which is 1. M is 2, gives you an exponent of 3, and then 5, and then 7, and so on. Okay, so this is the generating function of the number of partitions into odd parts. Now let's write down the other generating function that we're interested in, which is the number of partitions into distinct parts. Now, this is a little bit different. It's maybe a little bit less obvious how to extend this, or how to do this. So if you think about it, so every partition into distinct parts has either, if I look at how many ones does it have, it either has 0 ones in the partition, or it has 1 1. It can't have 2, because if there's 2 of them, they're not distinct. The parts aren't distinct. So that gives us a factor corresponding to the number 1, which is 1 plus x, because yeah, so the exponent, remember the exponent of x corresponds to the number of ones you have, and so it's 1 plus x. You either have 0, 2, or you have 1, 2, which gives you, for the second factor, you have 1 plus x squared, right? If I choose, so again, I'm choosing something from these things. If I choose the 1 here, it corresponds to having 0 ones in the partition. If I choose the x, it corresponds to having 1. If I choose the 1, it corresponds to having 0 2's. If I choose the x squared, it corresponds to having 1 2. And then next you have 1 plus x cubed, and so on. So again, this is, if you really understand what we did for partitions, then this shouldn't be a big jump in logic to understanding how you do partitions into distinct parts, right? Because you just take away all the kind of terms here, which would correspond to having more than one of a given number in the partition. So this is the product m equals 1 to infinity of 1 plus x to the m. Now this looks bad, kind of, right? I wanted to show that the generating functions are the same. I've got this generating function here, and I've got the one on the previous slide at the bottom. Those don't really look the same. Those look like different functions. But we're going to show that they're actually the same. So it takes a little bit of algebra and some canceling and stuff like that, but we're going to do it. But are we okay up to this point? So my whole goal in life right now is to show that this function is the same as this function. And then if they're the same, then these two sequences have the same generating function, and so they must be the same sequence. So here's a basic fact. I mean, I guess all of you know about differences of squares, right? This is, okay, it's not what, you don't learn this in kindergarten, but you learn this in high school at some point, right? If you have a difference of squares, so this is a difference of squares because it's 1 squared minus x to the m squared. Well, at least in Canada, you don't learn this in kindergarten, but maybe in some countries you do. They seem to always be ahead of us. Um, so, right, so if I have a difference of squares, I can factor it like 1 minus x to the m, 1 plus x to the m, right? Because this is x to the m squared. If I kind of monkey around with this a little bit by dividing by 1 minus x to the m, dividing both sides by that, what I get is that 1 plus x to the m is this ratio of 1 minus x to the 2m over 1 minus x to the m. So I'm going to use that because this is the thing, this is like the main kind of protagonist in my my second generating function, right? Like the generating function here is just multiplying up these 1 plus x to the m's. So I'm going to substitute this into my generating function. So what I get now is that I have the product m equals 1 to infinity, 1 over x to the m, that's what I started with, and I can rewrite it like this. Now, if you think about it, so if I have a product, so this is a product of a whole bunch of fractions. So it's infinitely many fractions, which is kind of weird. But here's what you know about products of fractions, right? If I have a over b times c over d, that's the same as taking the products of the numerators and the products of the denominators. So that's all I'm doing here. I'm just taking, if I multiply all these fractions, it's the same as multiplying all the top of the fractions and dividing by the product of the bottom of the fraction. And now I want to notice that stuff cancels. So to do that, what I'm going to do is I'm going to kind of think about writing out this product. So if you write out the top product, the first thing is 1 minus x squared, right? If I put m equals 1, I have 1 minus x squared times 1 minus x to the 4, 1 minus x to the 6, 8, 10, 12, and so on, right? All the even numbers. And on the bottom, I have all of the different 1 minus x to the m's. So I have, if I write out the bottom fraction, I get 1 minus x times 1 minus x squared, 1 minus x cubed, 1 minus x to the 4, 5, 6, 7, 8, 9, 10, etc. And you think about what cancels here. So on the top, I've got a 1 minus x squared, right? But I also have one on the bottom. On the top, I've got a 1 minus x to the 4, but I've also got one on the bottom. I've got a 1 minus x to the 6 here, and I've also got one on the bottom. The things that don't cancel are the odd ones on the bottom, right? This 1 minus x on the bottom isn't going to cancel because there's nothing like that on the top. And same with this one and that one, and so on. So what you end up getting is the product of 1 over 1 minus x to every odd number, which is, like we wrote before, 1 minus x to the 2m minus 1, where m ranges from 1 to infinity. But now we're happy, because this is exactly what we figured out was the generating function for partitions into odd parts. Okay, so what we've proven is that the generating function for partitions into odd parts is equal to the generating function for the partitions into distinct parts. So the generating functions are the same, therefore the sequences must be the same, which means that for every n, the number of partitions into odd parts is the same as the number of partition into distinct parts, which is, I think, kind of magical.